going to try some stuff with my webcam, and occasionally in the last few days, this has caused me to lose the video briefly. We'll see. I think it's going to be all right. Yeah. Can you guys kind of see that? That's going to be doing something like that, but much faster than you're seeing it do it now. All right, not too bad. Okay. Well, we'll see how this goes. I have a couple things. Let's see if this part works. This is sometimes when I lose the video. Okay, I think that's all right. Maybe a little bit of light there. Okay. Let's see. What is the goal for the next hour and a half or so? I don't know how much that time it'll take. The goal is to go through a couple demonstrations with the rotating stand behind me. I'll bring up the lab manual. I'll kind of do one or two example data sets, or I'll take a couple of bits of data live while you're watching the video, but then I mainly am going to just give you the relevant numbers for, I think there's basically in the lab write-up, it lists 7 sets of data. I'm actually going to give you 8 sets of data because half the data I'm going to give you was taken by me this morning. 4 of them, that's going to be part 3, which is the end of the data taking, back page or so of the lab. The other 4 data sets were taken by students last semester. And so I'm just going to kind of give you 4 that they took, which was using it was using the same basic setup, but it used a different spring, I believe, and probably things were arranged a little bit differently. So I don't want to mix my data with this apparatus, with their data. So I'm going to give you basically 1, 2, 3, 4 in the lab, and then that's from students' data last semester. And then I'm going to give you 5, 6, 7. I'm actually going to give you an 8th one, and I'll just ask you to add that in. Excuse me. I'll just ask you to add that in to the data set, and that's using the equipment here this morning, and I'll kind of show you a little bit how that goes. Let's see. I think most people are on here. We're up to 14 of you guys. So let me just kind of point to a couple files on Moodle that just recently got put up. Let's see, we don't need that. So today there's just 2. Last week, what were there, 4, I think? Yeah, this was last week. The lab and a couple other things last week. This week, I'll add a 3rd one to this, which is an Excel file, which will give you all of the values you're going to need. If you stick around, you'll probably be able to kind of get them off the screen just during the hour here. But there'll be a 3rd file here eventually, which will be an Excel file just listing, let me think how many pieces of data is. So for each of the parts of the lab, and for each data run, which like I said, I'm going to give you 8 sets. Each one of those will be 1, 2, 3, basically 5 pieces of data. I forgot. 3 types of data, but one is we take the measurement multiple times. So here's the 2 main guys here. So this is the manual, lab number 9, forces needed for circular motion. Don't worry too much about the numbering of these. Our numbering has changed. It's working out pretty well this week that the lab we're doing this week, forces needed for circular motion, directly overlaps and relates to chapter 8, which is what we started yesterday, and the homework is about for this week, which is about centripetal acceleration and a variety of circular motion phenomena. So that's helpful that we have a pretty good agreement. By the way, after today, we have 3 more labs. Basically, we had 6 labs in the first half of the semester. We're going to have 6 in the second half of the semester, and this is our 3rd one. since spring break. Um, and I will say this stand here is used for another one of the labs, not a week from now, but 2 weeks from now. Basically all the remaining labs are about circular motion or rotational motion, or oscillatory motion. We're going to have one lab about pendulums, and some other topics as well, but mainly about pendulums to wrap up the semester. That's getting ahead of myself, but I'm just thinking ahead. So here, let me show you what these guys look like. So this is the lab right up here, forces needed for circular motion. Gonna look at this here. Okay, I'm gonna read through some of this. Maybe make it a little bigger if you have this on your own screen. That's fine. An object moving in a circle has a changing velocity vector, so it is accelerating. What do we know about the acceleration? It points inward towards the center of the circle. Without a force to supply this centripetal acceleration, the object would fly off along a straight line tangent to the circle. So we know there's some inward force. If we see it moving in a circle, we know there's some inward force. And just the question is, what is the type of inward force? What is causing the inward net force and acceleration? This is something I really want to hit pretty solidly here. It is important not to think, I'm going to use the phrase centripetal force, or you're going to see FC written a number of times in the lab. It is important not to think of centripetal force, which is mv squared over r. It's important not to think of it as another type of force. In fact, any type of force can be the centripetal force as long as it is directed toward the center of the circle. So it's not like your free body diagrams include gravity, springs, normal force, and centripetal force. No. They include gravity, springs, normal force, and one of those forces will be the centripetal force. It's better really to think of it as a centripetal acceleration. I would much more often to myself, if we look down here, say AC, centripetal acceleration. And of course, what do we know about accelerations? We know that acceleration times mass equals net force. So if we have an AC pointing towards the center of the circle and you multiply by the scalar mass, you'll have a net force, or you could say centripetal force pointing towards the center of the circle. We know this equation. This is the key equation. If you do v squared over r, I would call it centripetal acceleration measured in meters per second squared. If you multiply this by the mass of the object, well, then it's a force. It's an inward net force or centripetal force, mv squared over r. So the goal of today's lab is to arrange for circular motion to occur, allow us to measure mv and r so we can calculate the prediction of this formula. And separately of measuring mass, measuring velocity, and measuring radius, separately, we want to measure the force like directly to test, does mv squared over r actually seem to do a decent job of calculating the force required? And the object, r is the radius of the circle, v is the velocity or tangential velocity with which the object moves around the circle. We're going to do uniform circular motion, so it'll be a steady speed all the way around, or nearly steady. Ideally, it'd be a steady, constant speed the whole time. How are we going to measure the speed at which an object goes around a circle? We're not going to directly measure speed. We're going to directly measure time. So I got my stopwatch here. So I have a scale that I use to measure mass, obviously pretty easy to measure mass. I have a ruler in centimeters that I use to measure a couple important radiuses. The radius kind of changes from one trial to the next. We use that to get radius. And stopwatch to measure time. What did we say yesterday? What did I say yesterday during class? If there's an object moving in a circle, radius, there's 4 ways to describe the motion, or 4 pieces of information to describe the motion. Radius of the circular path, period, capital T, time, which is the time to go around the circular path once. What else? Velocity and centripetal acceleration. And we said if you know 2 of those 4, you can calculate the other 4. So which 2 are we going to measure today? Radius and time. And then you can get velocity from distance over time. the motion is going to be pretty rapid today. It takes less than a second for this object behind me to spin around once when we're doing it the way when it's spinning at the speed we want it to. So I'm going to time 10 revolutions. So that's n is 10. So instead of 2 pi r over t, this is 10 times 2 pi r over the time. And you can think of that different ways. Basically, the time I give you, which is usually around 6, 7, or 8 seconds, the times I give you are not periods. They are 10 times the period because I'm going to time for 10 revolutions. So we need to measure mass, mass, radius, and time. And separate of that, we have to somehow determine the force independent of watching the circular motion. So we will test the centripetal force equation, mv squared over r, by making two sets of measurements, one while the object is rotating and one while the object is stationary. The rotating measurements help us calculate mv squared over r. The stationary measurements give us an independent check on the force calculation. The rotating measurement consists of marking the radial position and timing 10 revolutions of the bob. From that, we can find we have the radius r and the velocity. The stationary measurement consists of attaching the spring to a hanger. You'll see a spring here and a hanger, and adding mass until the spring is re-stretched to the same position it was in while rotating. So the rotating data and the stationary data are taken with the spring in a similar position each time. The gravitational force, okay, I'll get into that. The way we're going to test force C is we're going to measure something called capital M. I'm going to give you a mass capital M. There's 3 different masses in today's lab, by the way. Don't confuse the different masses. One of them is capital M. The force, the mass capital M times G is the experimentally observed force. Pretty easy. Mass times G. Which mass? Capital M times G is the force that we should compare to mv squared over r. Now, in parentheses right here, I'm going to come back to this kind of last thing I'll probably really talk about. There is a slight correction to capital Mg to account for the mass of the spring. This correction is described on page 3. So I think in the terminology there, it calls capital Mg F, and then it applies a slight correction, and it comes up with a slightly different force called F prime. So the actual comparison to the lab is not F to mv squared over r, it's F prime. And you'll see that this F prime stuff is worth doing, but it is a very, very small effect on your final numbers because it's taking into account the mass of the spring. And I'm going to give you the masses here just in a couple minutes. And you're going to see that the mass of the spring is not 0, but the mass of the spring is pretty small. Just remembered. The springs we're using, you guys have used once before in the Hooke's Law lab. In the Hooke's Law lab, you use these stiff springs, but you also use much flimsier, lighter springs. So we're using these stiff springs. This is actually the apparatus that the springs came with. Okay. Note that this lab involves 3 different masses, so pay close attention to which mass is being referred to. This black object here, right here, that's going to be swinging around. We're watching the motion of this black object as it swings around. That is little m, lowercase m, the mass of the rotating bob. And that is over 400 grams. So I'll give you the exact numbers. Actually, I can give you 2 of these numbers right now. So the mass of the bob is 458.34 grams. Now, occasionally we're going to add mass onto that, but that is the mass of the bob, lowercase m, for all of part 2 of the data set. So 458.34 grams for the rotating bob. Capital M is different for every trial, so I'm not going to give you that right now because it keeps changing. But mass of the spring, of course, that doesn't change. The mass of the spring is 16.20 grams. I'm going to put that in the chat here. So I'll give you these numbers here because they kind of get used a lot, but I'll mention them again later, maybe on Excel. Mass of, I'm going to call it the bare bob because later on in the lab we add slotted masses. You know, I kind of add a couple of these guys to the bob, but the bob without any additional mass added on is 458.34 grams. You can convert that to kilograms. That is lowercase m. And the mass of the spring, which is kind of like m underscore, pretend that's like like a subscript, m spring. This number is never going to change. It's 16.20. And I think you can see already, is the spring massless? No, because it's 16 grams, but it's attached to an object that's over 450 grams. So that's a pretty small mass ratio. So if we ignore the mass of the spring in today's lab, it probably wouldn't affect our results very much. What percentage is the mass of the spring compared to the mass of the bob? So as a percentage, I'm going to do 16.20 on my calculator divided by 458.34. And I got 0.035. So the mass of the spring is like 3.5% the mass of the thing attached to the spring. So that's not a very big effect. And we're going to see when you do some other, when you look at this corrected force calculation, it actually says you take that fraction, you take that ratio, and you divide it, you multiply it by 1/3. So 3.5% gets reduced to be more like 1%. So issues relating to the mass of the spring are by far the least important issues in today's lab. It's the least important mass because it's not zero, but it's pretty small. And just while we're here, I'm just going to mention this. Capital M equals the hanging mass, and that is different in every trial. So that's kind of part of the changing data as we go along. Okay. So I'm just going to give you like kind of look at this side view here. And then we'll do it up here behind me. Sorry, I'm going to switch to the other camera. So maybe I'll try to zoom in there a little bit. So there it is. It's just sitting on a little bookshelf. And where's my lab manual? Okay, so let's just turn this to look like that, you know, kind of like this. Now, right now, I think you can kind of see this. There's a spring here in the middle, and when it's rotating, this spring stretches. So I should probably kind of get it. When you're taking data, that spring is going to be kind of out like that. My whole tabletop is rocking a little bit. So that's the rotating mode. Or actually, I guess to make it look like that, I should turn mine around because I have the hanger over here and it's showing over there. Doesn't matter too much, but to make it look more like shown there, I'll do that. Okay. So this is little m. It's not a small mass, but it's the one called lowercase m. And there's a spring, and there's a string making it, attaching it to the bar. And you can see the silver counterweight on the far right. We're not studying the motion of the counterweight. We're studying the motion of the black tapered bob. And what is the tapered bob going to be doing when we're taking data? It's going to be moving in a horizontal circle. Okay. In a little bit, we're going to look at free body diagrams. How many forces do you think this black object is experiencing, at right now? It's not very many. Are we more interested today in vertical forces or horizontal forces if we're studying the circular motion? There's 3 forces acting on the bob, but there's only one horizontal force. And that's all I really care about today, because it's not moving in a vertical circle, it's moving in a horizontal circle. What's the one and only horizontal force on this guy as he's rotating? The spring. Which way is the spring pushing or pulling on the black object? The spring is pulling it towards the center. So the spring force is the centripetal force in today's lab. In other contexts, if you're talking about a satellite going around the Earth, the inward force is gravity. If you're talking about somebody taking a curve in a car, the inward force would be friction. We talked about vertical circular motion some other times, maybe with like the vertical loop a couple weeks ago in lab, and in that case, the inward force was related to gravity or normal force. Here, it's the spring. So the lab, each trial of the lab is to pick a distance right here at the top, pick a radius, and pick a Bob mass. So I can adjust the radius. I can adjust to make it smaller radiuses or bigger. The range is from about 15 centimeters to 21 centimeters. That's kind of like the lowest radius you can do and the biggest radius you can do. Here, I'll get it rotating at the big radius. To get it rotating at the big radius, it's moving faster. And what does the stationary setup look like? The stationary setup is to stop it, and then there's a string here that's just kind of stored for later use. Tangles. So it's to do this, and I'll show you that close. So the stationary setup, I gotta move a hanger here. The stationary setup is, there's a little string here, which you can probably barely see. And then you hang this off the edge of the table. Maybe I should move it over to get it off the edge of the table. You hang it off the edge of the table, and the hanger is 50 grams. I don't know how well you can see that, but it's there. The hanger is 50 grams, and then you can add a bunch more mass to that hanger. See that hanger hanging down? How much mass do I want to add to the hanger? I want to add mass to the hanger until this is straight below the support point, because I take data only when it's straight below the support point. And I think I'm going to back this up a little bit. So the key data point here is how much mass does it take on the vertical hanger to get it back to get this guy back to this nice position. We only ever take data in today's lab when this string up above is vertical and when the spring is horizontal. And you can see right now it's not a horizontal spring, it's angling upward, but it will be horizontal when I get to here. So how much mass do I have to add to this to get it there? And it's going to take a decent amount, actually. It's going to take a decent amount. I'll kind of show you here in a little bit how much mass it takes, but it takes hundreds of grams to stretch this down, 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 down to get it to like right about there. Okay. So I'm going to do a little set of data right now, and then we'll look at some free body diagrams, and maybe you'll see how all this kind of comes together. So each trial, I'm writing something here in the chat, each trial starts by choosing two things. One, a Bob mass, and two, a radius. So I'm going to choose right now just to do the plain Bob mass. I'm not going to add any additional 100-gram weights to it. Part 3 of the lab, part 2 of the lab, excuse me, is to only do the bare mass. So the Bob mass is the same throughout all of part 2 of the lab, and it's always the number I gave you up above. In part 2, Bob mass is constant and radius changes. And then guess what we do in part 3 of the lab? In part 3, it's the other way around. In part 3, radius is constant and Bob mass changes. It increases. So I'm going to do an example from part 2 of the lab. So I'm just going to say what's my choice for M? My choice for M is 458.34 because I'm not adding anything onto that. And I'm going to now measure this radius up top. Where's my rulers? So I'm measuring how far over this is, trying to measure it. And I go a little bit different. Okay, right now I'm just under 17 centimeters. I'm at about, so here's my example trial. Example trial, M equals 458.34 grams, and R, oops, sorry about that. Something grabbed my computer from me for a second. And radius is 16.8 centimeters. And I'm just going to do it here. Then if you look at page 2 or 3 of the lab, what is the core data that I need to take? I need to time 10 revolutions. I'm going to do that. That's called delta T. I would call that delta T. I'm going to time 10 revolutions, and it prompts you to do that 3 times. So kind of time it 3 times. I'll do that a couple times here. You guys can watch it. So I'm going to detach the hanger because I want to make this rotate. All right, here we go. Here's an example trial. Maybe I'll zoom out just a bit. And I'm going to get this guy rotating. What I'm going to do is I'm going to get him rotating so fast that he's beyond vertical. Like here, I don't know if you can see it very well, but this is further that way than straight below the sports. And as he slows down slightly, he'll kind of come closer and closer. And when he's nearly vertical, I'm going to take data on 10 revolutions. So if you can see that there, I'm telling you that's hanging a little bit beyond vertical, and I'm just gonna, oops, my guy's bobbling. Let me get it going faster. Okay, I didn't take data up here this morning because this is wobbly, but I'll take it here. So I'm letting it slow down. It's a little too fast, and I'm just letting it wind its way down. And when I feel it's nearly vertical, I'm gonna time 10 of these. And I think we're pretty good right about now. Here we go. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got about 7.37 seconds. So I would say, like, here's the example. Yeah, it did get moving pretty good there. Time number 1, 7.37 seconds. And then I'm going to do it again and a third time. little bit too fast. I'm letting it wind down. By the way, I'm kind of starting my time when it's over here. Okay. Getting close. Calling that good. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 7.06 seconds. And I'll do it a third time. I'll tell you, my times were more consistent when I did this better earlier this morning than that. That's not too bad of difference, but I think I can do better. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.10 seconds. 7.10 seconds, time 3. seconds. So that is almost all the data you need. That is enough data to calculate. An average time. Divide that time by 10 and find a speed. Do v squared over r and multiply by mass to get a centripetal force. So that's pretty good. That's enough to do kind of 1/2 of the calculations. And let's go through those right now. And then there's another data point to take for the stationary arrangement. I need to attach the hanger and find a mass, a capital M value. But let's just do the calculations right here. So first of all, what's the average time for my three? Data points there? So I'm going to take those, average them up. They're probably going to be closer together when I give you data later than this. I got, wrong number. I got 7.17, 7.1, about. So now I'm doing the calculations. Average time, 7.177 seconds. Okay, what's the next thing to do in the data table? So let's see. So bob mass, radius, time 1, time 2, times 3, average time. So what's the speed? Okay, how far did the object travel in 7.177 seconds? It went 10 revolutions, right? 1 revolution is 2 pi r, and 10 of them is 10 times 2 pi r. What was the radius? I forgot my own radius now. 16.8 centimeters, is that right? 16.8 centimeters. Okay, so I'm doing 10 times 2 pi times 0.168 meters divided by the average time. And I got 1.47 meters per second. And I would put that here in the speed. And then in the next table, summary table. So I have a radius, 0.168 meters. I have a speed, which I just said is 1.47 or 1.471 meters per second. Speed equals 10 times 2 pi 0.168 divided by 7.177. Whoops, 7.177. And I got 1.47 meters per second. Okay, next up is we do our main equation, mv squared over r. So now I use the mass of the bob, which was 0.5834 kilograms, times velocity squared. and then divide by radius, mass times centripetal acceleration, mv squared over r. And I came up with 5.90 newtons. Why does it do that? FC equals mv squared divided by r. And for those values, I got something in the 5.9 range. Okay, so that would be all the calculations for the rotating part of this trial. And now it's time to do the stationary part of the trial calculations. So what's the only real data point that I need to take in the stationary part of it? I have to attach the hanger and add mass to get this guy all the way below the support. So here I'll in the next 2 or so minutes give you that. I'll show you that. Okay. And where's my hanger? Here's my hanger. The hanger is 50 grams, and I'm going to add several masses to this. Anyone care to guess how much mass it's going to take to stretch it? It basically comes down to how stiff this spring is. The limpier the spring is, the less mass, of course, it would take. Let's see there if you can see the hanger there. So right now I have 50 grams for the hanger. This is 150 grams. It moved it over a little bit. Is it vertical yet? Is this vertical and that horizontal? No. Now I'm at 250 grams. I'm not yet vertical. Sorry, I'm going to try to hold something up here. I'm not yet vertical, so I'm going to 350 grams. No. 450 grams. I'm getting close, but I'm not quite far enough. Is it more than 550? Ooh, I think it's a little more than 550. I've added 500 gram weights to the 50 gram hanger. So I'm at 550. I'm going to try going to 650. And I feel like 650 is a little bit too big, so I'm backing off to 550. How about 600? That's 600. That's getting pretty close. Okay. So, what did it buy? I'm at 600. Ooh, okay. Oh, wrong one. Ooh, I'm at 620 right now, and I think I'm really close. I'll just think of one more number, and then I'll give you a measurement. Actually, maybe just under 620. 610. I think I'm going to call it 615 grams. I'm going to call it 615 grams. And right now, it's the range when I want. I always want to take data with the spring horizontal and the connecting strings, which are hard to see on the video, vertical. So hanging mass, this is the only measurement for the stationary mode, really. Hanging mass equals capital M is 615 grams. Okay. And what calculations do you do with this? Not very much. So I would put that in right here. I'm going to give you different numbers, but I'm just saying this is kind of how I would go about this. This is my capital M. What is my force? Well, it's pretty much mg. And I'm going to come up here, and here we go right here. Hanging mass, capital M. Bob mass, little m. Horizontal spring, horizontal rope, vertical rope. So what we should probably do is mg. So what is mg for 615 grams? That's 0.615 kilograms times 9.80. And I got 6.027. So my first thing is they call this F. Sorry. F equals mg, and I got 0.615 times 9.80, and I got a force a little over 6 newtons. Okay, now already we could do the comparison. How do you guys feel the comparison went? The centripetal force was 5.90 newtons, and capital M times G, which is another way to determine the force in the spring, is 6.03 newtons. How do you guys feel about that? I think I just got a call from Northwestern. So that wouldn't be too bad, right? But there is a slight tweak. And what is the slight tweak? This is the part of the lab that is, I'd say, least important conceptually and also least important numerically. I just calculated capital MG, which they call capital F, but then they say to multiply by this quantity right here. And I'm just going to read this description. We're going to go through it once. There is a correction for the mass of the spring, and it refers to a journal article that analyzed this situation in the 80s. This correction is needed because the spring is not massless and has a natural tendency to lengthen as it rotates. So don't just do capital MG and stop there. Do capital MG and multiply by this thing in square brackets. And for the first and only time in the calculations for this trial, I have to use the mass of the spring. Can you guys calculate what this number is in square brackets? Don't do the mg yet. Just what's this number in square brackets? 1 minus 1/3 times mass of spring over mass of bob. Well, we already said the spring over the bob is about 3.5%. I can calculate it again, but it's about 3.5%. And then you divide by 3. So this number right here is a little over 1%. And then you subtract from 1. So the number in square brackets is somewhere around 98% or 99%, and I'm going to calculate it right now. I'm going to do 9883. It's something like that. 1 minus 1/3 times, and what is it? 16.20 for the spring, and 400. I forget the number, 458.34 for the bob. And it turns out to be divided by 458.34 divided by 3, 1 minus. I ended up with 1 minus 0.0117 or 118. So I ended up with about 0.9882. 4 digits. Does that sound about right? Oh, I got a number pretty similar to you, Daniel. So 0.9882. By the way, what are the dimensions of this number? Did it again. What are the dimensions of the number in square brackets? Grams over grams cancels out. This is dimensionless. So take mg and multiply it by 0.9882 or so. So my corrected force, what they call the corrected force, because it involves this subtle correction, they call that F prime, and that should be 6.03 times 0.9882. And I got, it barely changed it, but it changed it to be 5.96 newtons. Okay, so that is basically what we're going to do here. We're not quite going to compare mv squared over r gave us 5.90. Capital MG gave us 6.03. If you compare those, that's basically what the lab's about, but we're not quite doing that. We're going to do 5.90 compared to 5.96. And how well did that work? I don't think they're all going to work this well, especially because I didn't really take much care in taking the data as I did this on the video. But the goal is to really fill in summary table 1. And I would get a mv squared over r of 5.90, f prime of 5.96. What's the percentage difference? Centripetal minus f prime over f prime. So 5.90 minus 5.96, they differ by 0.06, divided by 5.96 times 100%. And I actually got negative 1.0%. They differ by, this value is smaller than this value by 1.01%. 1.0% really, which is, I don't think they're all going to come out that good, but I got a percent difference of negative 1.01%. I don't care too much about the minus sign. It's just saying that FC was smaller than F prime. I would expect generally you're going to get percent differences. Let me look around here. I think you're generally going to get percent differences like probably generally less than 5% error difference. So hopefully we feel fairly encouraged about this v squared over r stuff, because v squared over r led to the prediction of 5.90 newtons, and we pretty much measured it fairly directly and got a number either just over 6 or just under 6. Not too shabby. And we're going to do that 8 times. 4 with the same bob, changing the radius, and then another set of 4, although there's only 3 rows on the table, I'm going to give you 4 sets of data. Another set of 4, which is the same position, the same radius, putting more and more mass on the hanger. More and more mass on this black thing, because there's a way to attach additional masses to it. Are there questions kind of about how that goes? So the analysis is to basically calculate FC in the summary table, F prime in the summary table, and the percent difference. And if you do that for every trial, that is the culmination or the goal of the analysis. And the intention is to see how well does mv squared over r do in predicting the force required from the spring to get circular motion. 2 more things. Oh, sorry, somebody just asked a question. I missed it. All the data we need will be on the Excel sheet. Yeah. So what will be on the Excel sheet, I'll kind of start to write it up here, and I'll probably, you guys could watch me write it up, or you could kind of sign off maybe in like 10, 15 minutes here. And then you could just get the Excel data. But for every trial, I'm going to give you a bob mass. I'm going to give you a radius. I'm going to give you 3 times for 10 revolutions. So time 1, time 2, time 3. And that's all the data for the rotating arrangement. And then in separate of that, I'm going to give you what the hanging mass capital M was in the stationary arrangement. And somewhere in there, I'll mention the spring mass, which is used kind of throughout. I would expect maybe within about 5% issues, 5% error types of issues. One other thing I want to look at here, just to solidify this. So, the radius is bolded, centripetal force, FC is bolded, actual force, F prime is bolded. Those are the core data. And then I guess percent difference could basically be bolded again. In looking at this data table, there's really kind of a couple chunks to it. The first 3 columns are related: radius, speed, centripetal force. And then I'd say I would almost put like a heavy bold line right here, like to separate the table at this point, because hanging mass and actual force are very closely related. So these 2, are part of the stationary arrangement. The first 3 columns are the rotating arrangement, and the percent difference is to compare the stationary arrangement to the rotating arrangement. What is part 3 of the lab? Varying the bob mass with a constant radius. It says to choose one of the radii from part 2, and I'm not going to do that. I'm just going to give you a different radius. perhaps one of the middle values. I can tell you the radius for the constant radius for all of part 3. It'll be in the Excel table, but the constant radius for all of part 3 is, it's written right here, 18.1 centimeters. So I sat at 18.1 centimeters, similar to what you see behind me, and I did it with just the bare bob. I did it with the bare bob plus 70 grams, the bare bob plus 130 grams, and the bare bob plus an extra 200 grams. And that's kind of the most I could fit on the object. So I'm going to give you basically a 5, 6, 7, and 8. The bob mass is 458 and going upward, time, and you can convert this, you can carry it all down to here. What's the only difference between summary table 2 and summary table 1? Whoop. Summary table 1 has different radiuses and a constant bob mass. Summary table 2 has different bob masses and the same constant radius. And one of them only has 3 rows, but I'm going to give you a 4th row. Okay, here's the other thing I'd like to look at or point you to. This is the other file on Excel. Forces needed for circular motion PDF. FBDs, free body diagrams. Looks like I'm jumping around. I don't know if you guys can hear me. How's it working? Okay. Okay, going back. So what did the free body diagram sheet, what does the free body diagram sheet look like? You know, this is, let me see here. Okay. So we got some free body diagrams here. When you're rotating, this is the rotating one. Rotating data, MR delta T. When you're rotating, what's the free body diagram? There's the vertical string upward. I'm going to call that T1, I guess. There's the gravity force downward. And I don't care too much about those because T1 and FG1 are equal and opposite, and that takes care of the vertical dimension. I care about the horizontal dimension. There's a horizontal spring force, and that is the only horizontal force on the object when rotating. So the horizontal spring force is the net force, and the net force has to equal mass times acceleration. So Fs equals ma, and we know that acceleration, this is what we're testing, is the red formula. Acceleration should be inward towards the center of the circle, like towards the spring basically, and v squared over r. So spring force or centripetal is in the rotating arrangement, spring force is the centripetal force mv squared over r. What about in the stationary arrangement? T1, FG1 cancel out. How much acceleration is there when it's stationary? You can see it right now behind me. Of course, there's none. So spring force one direction is balanced by the tension in this connecting rope, which is going over the pulley. This would be the pulley kind of right here. It's going, this T2 is the horizontal rope that's going over the pulley to the vertical hanger. So T2 equals Fs when we look at the horizontal forces for the bob. But if we go around the pulley, we get to another free body diagram, very simple. T2 is pulling up on the hanger, which you can't quite see behind me, I don't think. And what's pulling down on the hanger? Capital MG is pulling down on the hanger. So in this case, Fs equals T2 and T2 equals capital MG. So the spring force is capital MG, which they call the measured force. And we're pretty much going to compare these two. What's the only tweak? We're going to take the measured force and we're going to multiply by that number in square brackets, which will change it by like less than 2%. So we don't actually do F to FC. We actually do F, change it to F prime, which changes it very minimally as a number, and then compare. Questions about the free body diagrams here? You could unmute your microphone, or I think I'll see if a question shows up in the chat, but I'll check back. This is an unbalanced force resulting in acceleration, keeping the object going in the circle. This is for balanced forces, and sure enough, it's stationary. All right. Okay. So let's see, what time is it? We've been going for about an hour, about 50 minutes or 55 minutes. I think that's what I was going to say. If there's questions, I would ask them now. And what I'll do after this is I'll start to bring up an Excel sheet and I'll start to kind of write the numbers in there. And you could either, wait around and kind of see those as I fill them in, and then I'll add that to the lab number 9 folder for this week on Moodle. All right, just waiting for questions. Let's see. Couple reminders about this week. Last week's lab is due. It's this. What all do we need for last week's lab turn in? Just the 2 worksheets and the Excel sheet. Yes. So I'm imagining like kind of one PDF of the 2 worksheets, or maybe there'll be images, separate images, but either 1 or 2 files for the 2 worksheets, and then 1 additional file for the Excel sheet. That's what I would submit to to Moodle. And it says that's due by noon. Or I don't remember what time it is. I think I said noon. If you send it in the afternoon, that's fine. I'll just see a little note saying when it was submitted, and that's all right. We don't have class tomorrow. We're going to have no class on Good Friday, and like I said yesterday, maybe look for something over the weekend. I'm looking out the window, and it's snowing pretty good where I am. Wow. It's snowing pretty good. We'll have something on Monday, some video or something, talking about, in our case, talking about gravity, chapter 13. Lots of capital G calculations coming up. Is homework due Friday then? For this week, I made it due next Monday at the end of the afternoon. So if you had questions about this week's homework, you'd have a chance to ask them on Monday during class. Generally, on a general week, if it wasn't Good Friday, I would have homework due at 6 o'clock Friday, and you'd have chances during Friday class to ask questions. In this case, we're going to make that Monday at 6 p.m. All right. Have a good Friday. Have a good Friday. Have a good Easter. Did want to mention one other thing. I don't know if you've gotten an email yet, but there'll be an email from the administration about some grading options that students are going to have for classes for this semester because of the great disruption of the coronavirus. So maybe you can look for that in the next couple days. We talked about it at the faculty meeting on Tuesday, and I think it was going to be kind of finalized and communicated to students pretty soon. You're going to have a chance to kind of change your grade status from graded to like pass, no pass, and it'll be just for this one semester. I would say you're all doing pretty. I have not graded the tests yet. You'll get those over the weekend. You're all doing fine as standing in class, but maybe just a heads up about an option that you might want to think about for some of your classes this semester. Also, a lot of the faculty and staff is taking a day across the state of Minnesota, and University of Northwestern is participating as a day of prayer and fasting, just to pray for the national and global situation. Just something to think about. Maybe you've heard something about that, or maybe you're aware of other Christian or church groups you might be connected with that are doing something today on behalf of that. I only heard about it through Northwestern on Tuesday. Otherwise, I probably would not have caught that news. All right. If you want to hang in a little bit, I'll start to make an Excel sheet, and you'll see kind of what it's going to look like. But in general, you guys have gotten what you want to see, you need to see, and you're dismissed if you want to head out. Let's see here. So you should convert grams to kilograms, by the way. So I would say convert grams to kilograms, convert centimeters to meters, seconds will be seconds, and if you do that, all your forces will come out in the standard unit for force, which of course is newtons. So oops, messed that up.
Hey, excuse me, Professor.
Yeah, I'm listening.
Um, I was wondering about the experiment project that we were working on before spring break. Is that still going on, or is it pretty much terminated?
Well, short answer is the projects you were working on before, whoops, dropped a little mass on the floor. Projects you were working on before spring break, that's not going to occur. What I think we're going to do and what I'm going to decide over the weekend is I think we're going to have some kind of research project substitute. So something that you could do together with the lab partner or lab partners that you were going to do the other project with, but instead of an experimental based project where you'd actually be able to carry out the interesting ideas you guys had planned with actual hands-on equipment, I think we're going to change that to be, I'm going to kind of give a list of topics, suggested topics that people could kind of do a little bit of research on and report back about. What I would like to preserve about the projects is I would like to preserve, well, a couple things. We're not going to be able, I don't think, realistically, to do the hands-on stuff because we're all spread out in different places. What I'd like to preserve that I think we can, though, is the presenting of information to the rest of the class. Because if you remember the way we were going to do it, the semester would have, that research project that we worked on throughout this, that you worked on throughout this semester, would have culminated in a poster presentation in the last week of the semester. And I think I would like to have still some presentation component to our lab projects, but in this case, the presentations will be on probably more kind of internet textbook research of some topic related to Physics 1201. What do you think about that?
Okay, I just wanted to know what
Yeah.
the plan for that was.
Yeah, that's a very helpful question, Preston, for everyone who got to hear that, which is 4 other people. So thanks for mentioning that. I think I'll say something about that next time we have class together, which I guess is next Wednesday. Maybe I'll mention something to the lab section too in half an hour here or an hour.
Okay, so
Yeah. So something like that, and I'll have more of a plan by next week.
And also with the tables,
Yep.
do we need all the timing tables and the other ones in the same Excel document? So it's gonna be like a giant one with all the different points.
I would probably recommend having all your data there. Basically, there's 2 tables for each part. There's one table that just has positions, times, and velocities. They call that the timing table. And then there's a summary table, which has basically information that helps us calculate force. So I would imagine if I were you, I'd probably do something where part 2 timing table, and next to it part 2 summary table, and then part 3 timing table and summary table.
Okay, too easy.
Yeah, you could put it all into one big table. You could just be one long table for every trial. If you did that, that'd be fine, because that's kind of in effect what it's going to look like. It just on the page they kind of split it up into one table that has a bunch of times building up to a speed, and then carry that speed over and put that speed into the other table and have the other information there.
Okay.
Yeah. All right. So so here's the radiuses. I'm actually going to put some numbers in there. Oh, where are they? Okay. Oops. Whoa, what happened there? Forgot. 4 centimeters. Oops. It's supposed to go this way. Um, hanging mass. Whoa, wrong way. Okay. That is pretty much it.